Okay, in the last video we saw, for instance, phi is a scalar in which is a tensor, a zero order tensor. It's a scalar. Then a vector v is equal summation I is equal 1 to 3 of vi ei. Okay, this is a vector of first order tensor, and a second order tensor we have I is equal 1 to 3 summation j is equal 1 to 3, for instance a I j ei ej. And then, okay, you have a third order tensor. You have 3 summation over here. Okay, that's k is equal 1 to 3, I is equal 1 to 3, and j is equal 1 to 3. Okay, of a I j k, e I, e j, and e k. So and so on. Okay, that's a second order tensor, second order tensor, and this is a third order tensor, okay, and so on. Now our convention is this. This is a first order tensor. There is only one unit vector here, over here. This is a second order tensor, 2 unit vectors, and this is 3, and so on. So our convention is just to work with the component. So a first order tensor, you have one free index. Here we have 0, 0 free index. Okay, a scalar has a 0 free index. This is one free index. Here you have 2 free index. This is 3 free index. Now, for you to understand, okay, to feel the idea of free index, suppose I have here 3 boxes. Okay, this is for I is equal 1, I is equal 2, and I is equal 3. This is V1, V2, and V3. So I'm free to choose any of these 3 quantities. That's why we say here that I is a free index. If Aij, I have 9, okay, 9 elements, okay? I have 9 elements. For instance, this element here is A12, for instance. The last one will be A33. Again, I'm free to choose any of these elements. That's why they are called free indices in this case. Okay. Likewise, this I have 27. So I have elements here, and these boxes, and then the last one. So this element here, for instance, is A111. This is A112, for instance. Okay. Then we are free to choose, okay, any of these elements. That's why they call free index. Now you see that a scalar, we have only one box. For instance, we say a mass here is at 20 pounds, okay? 20 pounds. That's a scalar, okay? I have only one choice, okay? A vector will have three choices. Obviously, we are talking about the space R3, okay? That's why I is from 1 to 3, J is from 1 to 3, okay? That's a way, okay, you see how easy it is to identify free indices, okay, in expression, okay? In linear algebra, the product of matrix A and B, okay, the product of AB, okay, let's call C, okay. Obviously, when you study linear algebra, the matrix A, let's put over here, product of A and B. Here we have M by P, this is M, P by N. So this same dimension here has to match. So then I have C will be M by N, okay? So we can only multiply matrix, okay, if this dimension here matches with this dimension. So M is a number of rows, P is a number of columns. In matrix B, P is a number of rows and N is a number of columns. Now, how can I get an element Cij? Okay, this is summation of A, Ik, B, Kj. Now, this summation for K is equal 1 to P. Okay, that's the element of the matrix. So let's develop this. Okay, now K1 to P. Okay, then I have C is equal A, I1, B1, J plus A, I2, B2, J, and so on. Okay? And the last one will be A, I, P, B, P, J. So if suppose I have a matrix, okay, let's put 2, 3, 3. This is -1, 0, 2, 0, 0, 1. This is a matrix 3 by 3. Suppose I multiply by a column matrix. Okay, let's put here 0, 2, -1. This is 3 by 1. You see, these 3 here matches. So the result will be 3 by 1. You see here, it will be 3 by 1. Now, suppose I want this element over here. Okay? There are 3 elements over here. So 3 rows and 1 column. 3 rows and 1 column. Suppose I want this element over here. Okay? Now, what I want is C to 1. This element here is C to 1. Okay? So, this will be the product, the sum of the product of the second row times this first column. So, this is equal to -1 times 0. I'll put over here, C to 1 is equal -1 times 0 plus 0 times 2 plus 0 times 2. Now, plus 2 times -1. Plus 2 times -1. So the element here will be equal to, this is 0, 0, this is -2. Now, I'm free to choose this element or this element or this element. That's why here we have 2 free indices. okay? Because I'm free to choose, okay? And this is a matrix multiplication. Just for you to understand, okay, what means free indices. Another example. In R3, suppose this is x1, x2, and x3, okay? Now, suppose on each point you have different temperature, okay? For instance, at this point here, or at this point here, we have a temperature, okay, which depends on x1, x2, and x3. Okay, that's my temperature. Now, observe this in another point. Okay, I have another temperature over here. Now we see that the temperature depends on this point here, because if I change the point, the temperature will change. Suppose that. Now I want to find out. Suppose the temperature behaves like that. Let's put x1 square, x2, x3 to the power 5. Suppose. Okay? Now, I want to find out the derivative, partial derivative of temperature with respect to x1. You see? This is 2x1, x2, x3 to the power 5. Suppose I want the partial derivative with respect to x2. See, temperature is scalar, okay? But depends on the point. Now, derivative with respect to x2 will be x1 square, x3 to the power 5. And also, suppose I want the temperature with respect to x3. So this will be 5 x1 square, x2, x3 to the power 4. What you see that the temperature is scalar, but the partial derivative has one free index. Look, suppose then I write partial of t with respect to xi or xj, or I put xk, okay, no problem. This is one free index. This is one free index. Now, I can put 3 boxes over here, okay? And this one, I put the partial of t with respect to x1. This one, partial of t with respect to x2. Partial of t with respect to x3. So, we look here and we guarantee that there is 3 boxes, okay, in which I'm free to choose any of these. Okay, so temperature is scalar, but the partial derivative of t with respect to xk, okay, obviously k is 1, 2, or 3. Okay, just for you to understand how it's important to work with the tensor notation. Okay, I just write partial of t with respect to sk. In tensor notation, when you have a partial derivative with respect to xk, you just put this partial derivative with respect to xk. This is another symbol. We just put comma k. Okay? When you see in the tensor notation a comma here, it means that's a partial derivative of t with respect to xk. Okay? Now consider that I want the partial derivative of the partial derivative. Okay, is the second partial derivative. Okay, now let's erase here. let's erase here. So, then suppose I want a derivative of this term over here. So, partial derivative of t respect to x1 respect to x1. So I'll derive again respect to x1. So this will be 2 x2 x3 to the power 5. This is x1. Now, a partial derivative of this with respect to x1. So partial derivative with respect to x1 of, in this case, of t with respect to x2. Okay? Now, I'll get the derivative of this with respect to x1. So it'll be 2x1, you see, because it's square, x3 to the power 5, and so on. Now you see, in this case, we have a tensor of order 2. Oh, look, this is a tensor of order 2. So here I can write, I'll put here partial derivative, okay, of xi, xj. Okay. Now, for I is equal 1, j is equal 1, I have this. For I is equal 1, j is equal 2, I have this, and so on. So then I can write here as t, comma, ij. See? So again, the temperature is a scalar. The first derivative, we have only one free index. Now the second derivative, we have two free index, okay, or two indices, okay, two free indices. Then it is a second order tensor, and t is a first order. Let's write here, okay, the second order tensor. Actually, as I said before, we talk about tensor looking at the elements, okay, forgetting the unit vectors, as we said. Here is a vector, okay, there's a first, behaves like a vector, okay, is a first order tensor. This is here two free indices. Here is one free index. Okay? This is one free index. And so on. You see, you have several results here. Actually, you have 9 results. Okay? But from the calculus, this behaves the same as this. This is x2, x1. We can make a permutation here, the results will be the same. So this will be a matrix called symmetric matrix because for instance, Cij is equal to Cji. Okay? In this case over here, okay, you have a symmetric tensor. In our course, Vector and Tensor, we define a dot product, and then using the components in x1, x2, x3, the components in the standard basis, okay, this is E1, E2, and E3. Okay? So then A dot B is equal, okay, A1 B1 plus A2 B2 plus A3 B3. Okay, in linear algebra, I'll put capital L. In linear algebra, we can deal with Rn. Consider Rn. This is R3. Okay, this is R3. Now, the dot product is called inner product. So when you study linear algebra, the dot product, okay, for R3 is called inner product. So you generalize this summation here. So this is a sum of I is equal 1 to 3 AI BI. In linear algebra, what you do? You have a row vector, and this is a column vector. You can see here, for instance, if you have this row, you have, for instance, I put capital letter, A1, A2, AN, okay? Now, here, B1, B2, Bn. Here you have one row and n columns. Here we have n rows and one column. I put the dimension over here. Okay, this is 1 by n. This is n by 1. You see, this number here matches. So the result is 1 by 1. So the result here is 1 by 1. 1 by 1. It's a scalar. Now, this number here is just A1, B1 plus A2, B2 plus AN, BN. This is a number. This is a number. Okay, I erase here just to. This is A1, B1 plus A2, B2 plus AN, BN. This is a number, okay? This is a scalar. There's a number. The matrix here is 1 by 1. It has only this element. Suppose in linear algebra, consider Rn, I want to put here A1, A2, AN. This is a column, and this is a row. Okay, in Rn. You can see what is the dimension of this column here. I have n rows by one column. What is the dimension of this matrix here? Is one row by n column. You see, this is one column, two columns, and n column. So here I have a matrix, okay, in which you see this one here a match. So the result is a matrix n by n. Now, a square matrix, you see, because before the product was a row times a column. Now it's columns times a row. It's different, okay? A row times a column, as we did, just we did before, is one element, is a scalar. Now, the column times a row, okay, is a matrix n by n. So look, first row, first column. So this is A1, B1. Now, first row, second column, A1, B2. First row, nth column. So this will be A1, Bn. Now, second row, first column, A2, B1. Second row, second column, A2, B2, and so on, okay? Now, the last one will be AN, B1, AN, B1, the AN, B2, AN, B2, and AN, Bn. Okay, in linear algebra, this product is called outer product. Okay? We can write the outer product in terms of the standard basis. Okay? But the standard basis in Rn, like that. Let's put over here. Okay? Look. I write I put AE1 plus AE2, let's put A1E1, A2E2 plus AN EN. Here is B, B1E1 plus B2E2 plus BN EN. Okay? That's a vector, and this is a vector. Now, this is equal, look, A1, E1, B1, E1. So this is equal A1, B1, E1, E1. Plus, now, A1, E1, B2, E2. A1, B1, E1, A1, B2, see, A1, B2, E1, E2, plus, and so on, okay? What you see here, okay, this is I'll raise it here, okay? You see, all the elements of this matrix, n by n, is right over here. So, these are the components of this tensor over here. This is a tensor, see? That's a second order tensor, okay? In Rn, okay? Now, these are the elements of a second order tensor, right here. See this equal here? Is this? This is a tensor A, B, or we call outer product. So, this is a tensor is equal a vector and a vector. Okay, that's called C. Just put two bar over here. That's a second order tensor. So the outer product, okay, is a second order tensor. The inner product is a tensor, but order 0. Okay, the outer product is a tensor, okay, and order 2. Now, because we are working in the R3, you just stop here. You see, you just put here. See, this is A3, E3, and here will be B3, A3, and this instead this is 3 by 3. Okay. Now, we see that the outer product, because in the literature, in the videos, you find inner product, outer product. You use inner is a dot product in linear algebra when you work in the Rn space. And outer product is when you just put one vector next to the other, okay? There is no sign here, okay? That's why we have a second order tensor. Okay? If you put a dot here, you'll be a dot product. Okay? Let's see the Kronecker Delta. In R3, you can also work in Rn, no problem. So let's write x1, x2, x3. This is E2, E1, and E3. This is ortho, normal, basis. Okay? What means that? EI dot EJ is equal, will be 1 for I is equal J, and 0 for I different from J. We saw this. This is what you call delta Ij. So you can write here delta Ij. Delta Ij, okay? In linear algebra, this is an element of the identity matrix. What do you mean by identity matrix? You have 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. Okay? That's my identity matrix. So this delta Ij is an element. Okay, look, how many free indices we have here? 2. I choose any of these. For instance, delta 1, 2. Delta 1, 2 is 0. I'm free to choose. Okay, it's 9 elements. See, this is 3 by 3. You have 9 elements. Okay, I'm free to choose any of these. For instance, delta 3, 3. Third row, third column is 1. That's why this is a second order tensor. Now, this is delta Ij. Now, what do we want to calculate now is this delta Ij, Aj. Now, this is a second order tensor. This is the first order tensor. But when you adjoin them, okay, this whole thing here, this is a vector. Why is a vector? Because here we have only one free index. One free index. That's why it's a first order tensor. This behaves like, it's better to do this. The first order tensor. I'm free to choose for I is equal 1, or for I is equal 2, or for I is equal 3. That's why it's one free index. Let's develop this, okay? Now, delta I. This is a summation, okay? There's an Einstein summation here. JJ, you see, will be 1, A1, plus, you see, there's a dummy. J, I'll write later, okay? J is a dummy. So, this is delta I2, A2, plus delta I3, A3, okay? Because the dummy, J is equal 1, 2, 3, that's the sum. This here is the same as summation, J is equal 1 to 3, delta I, J, Aj. This is the same, but because we are using Einstein notation, you just forget the summation, so you see the sum of J. Now, I'm free to choose I is equal 1, or I is equal 2, or I is equal 3. Suppose I want I is equal 2. Delta 2, 1 is 0. Delta 2, 2 is 1 because I is equal j. And delta 2, 3 is 0. So for I, let's erase here. Look, that's a very, very important property of the Kronecker Delta. Now, for I is equal 1. I put that I is equal 1. Okay. Now, delta 1, 1 is 1. This implies I'll put delta 1, 1, A1, plus delta 1, 2, A2, plus delta 1, 3, A3. I just wrote for I is equal 1. You see, this is 1 here, okay? I is equal 1. 1 here, 1 here, and 1 here. See? Now, this is 0 from here. This is 0. This is 0. This is 1. So this is equal A1. Now, let's come to I is equal 2. Okay? For I is equal to delta I is equal to here. You see? Delta 2, 1, A1 plus delta 2, 2, A2 plus delta 2, 3, A3. Let's see. Look. I is equal to, this will be 2, 2, and 2. Now, this is 0 because I is different from j. This is 0 because I is different from j, but this is 1, so this is equal A2. Now, I is equal 3. Delta 3, 1, A1 plus delta 3, 2, A2 plus delta 3, 3, A3. Let's see. I is equal 3. I is equal 3. This is 3, 3, and 3. This is 0 because I is different from j. This is 0. This is also 0. And this is 1. So this is equal A3. A very, very important result. Delta ij, aj, okay? This behaves like you go in this j here and put I. AI. Look, for I is equal 1, A1. For I is equal 2, A2. For I is equal 3, A3. So delta ij, aj is AI. See? And I'll put here this to be clear. 2 and 3. See? I is equal 1. I is equal 1, blue, A1. I is equal 2, A2. I is equal 3, A3. That's a very important result that we're going to use. That's I would say, is a main property of delta ij. Okay? You look, you see the free index, okay? You take the dummy, okay, and out, and put I in this place here. Calculate delta ij. First of all, what is delta ij? Is a second order tensor. What is delta ij? Is second order tensor. what's the rank or order of this tensor over here? This is a scalar. Why is it a scalar? Because there is no free index here. See, look. There is no free index. I is dummy and J is dummy. Okay, suppose I put like this. Look, delta KP PK. Suppose the same results, because K is dummy and P is dummy. If it's dummy, doesn't matter. I put MN, QP, no problem. See? The same result. Let's IJ. Now, I could develop this, okay? But I will use this property over here, okay? Look, delta ij, forget that this is delta, okay? Look, delta ij, choose one or I or j, and put I or j, like this. I will do, look, delta ij, delta ij is equal, look, delta ij, you see delta ij, suppose aj, okay? I take out j and put delta ii. You see, look, delta ij, there is no delta on the right hand side, you see, delta ij, okay, the j disappear and will go there to I. Here, j disappear and then go to I. So this is a scalar. This delta 1, 1 plus delta 2, 2 plus delta 3, 3. You see that this is the trace. Trace is the sum of the elements of the diagonal, the main diagonal. Okay. Now this is my identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. This is delta 1, 1 plus delta 2, 2 plus delta 3, 3. This is equal to 3. This is 1 plus 1 plus 1. A scalar. See, this is scalar. Okay? Scalar. You see, these I could develop this. Okay? I have two summation here. Did you imagine this? Look, I put here summation I is equal 1, 2, 3. Then summation j is equal 1, 2, 3. Delta ij, delta ij. You see? I developed this and use the definition of delta ij. I will find 3 here.